So, now I mean staring at this particular example, right. So, so because we have introduced this dominant pole omega d, which is much smaller than omega naught, right. Okay. The loop gain function approximates that of the response of the loop gain basically approximates that of a first order system, and therefore, the closed loop, and so you basically get now the stability of a first order system, right. Truly it is actually a fourth order system, right, but what this is telling us is that since the poles omega naught are so far away, right, for all practical purposes this is looking like a first order system, right. And why do I say for all practical purposes? So, basically you can see that when these higher poles kick in, which add extra phase, which can potentially make the angle of the loop gain equal to 180 degrees, right, the magnitude has become so small that 1 plus that loop gain function, whatever you add, right, if the phase is 180 degrees, but the magnitude is so small that denominator can never become 0. Does it make sense, right? So, for all practical purposes this looks like a first order loop gain function, right, which then therefore means that the the 3 dB bandwidth of the closed loop system will be A naught cube f, what do you call the 3 dB bandwidth will be A naught cube f omega d. So, here we have a situation which we wanted, namely that we have the high DC loop gain corresponding to a third order system and the stability properties corresponding to a first order system, right. Okay. Now, the question is, what have we lost in the bargain? I mean, you know that there is no free lunch, right. So, what have we lost? See, in the original system, remember that the loop gain function was high up to a frequency of almost omega naught, right. Okay. But now what is happening? You know, at frequencies way below omega naught, correct, we basically see that the loop gain is already reached, has already fallen off to 1, right. Okay. So, so you know, one could of course complain that well, in this whole process, you know, earlier we had this loop gain magnitude which is very large for up to very high frequencies, and now you know we end up in a situation where the magnitude response, or the magnitude of the loop gain has fallen off to 1, right, at frequencies way below omega naught. Remember that if you want this omega naught not to bother you at all, right, these poles at omega naught not to bother you, the unity gain, what comment can we make about the unity gain frequency versus the location of all these extra these poles at omega naught? Let me repeat the question. If we did not want these extra poles, I mean these poles at omega naught to bother us in any way as far as stability is concerned, what comment can we make about the relative position of the unity gain frequency, which is A naught cube f omega d, versus these poles at omega naught, versus omega naught? Pardon? Far apart, which is smaller? Yeah. So, basically, you know, to make this look like a very good first order system, you must choose the unity gain frequency to be way smaller than the omega, the location of the higher poles. Does it make sense? Okay. So, therefore, you know, what we have paid in order to achieve the stability is that what you have paid in order to achieve stability is that, well, bandwidth has gone down, right. Well, but this seems like a reasonable trade off, because I mean, you know, you earlier had a system which was unusable because it was unstable, right. Now, well, you have a system which is usable, right, and you know, and you have the high DC loop gain that you want, right. So, this is the basic idea behind dominant pole compensation, right. So, now the question is, okay, well, now what if, for instance, you know, in this example I chose this, let us say I chose this dominant pole frequency to be omega d1. What if I had made another choice, omega d2 like this, okay. So, this is another choice of dominant pole frequency. This is another choice of dominant pole frequency, right. Here also this is A naught cube, what is that? A naught cube f omega d2. Here also at the frequency that the higher order poles kick in, alright. The magnitude, what comment can we make about the magnitude of the loop gain function? It is also less than 1, right. So, you know, for all practical purpose, this also looks like a first order system. So, now the question, but what is the advantage of choosing omega d2 over omega you know d1? Well, the unity gain bandwidth is evidently increased by some factor, correct, okay. So, there must be a way of quantifying, I mean, which of these systems omega d1 versus which of these two choices of dominant pole frequency, omega d1 or omega d2, which of them, you know, make the loop gain a better approximation to a first order system? Omega d1, because the you know it is the frequency at which you know the higher order poles kick in, at that frequency the magnitude is much smaller, correct. So, there must be some number or some metric to be able to qualify, you know, how close to a, you know, true first order system the dominant pole is making the system look like. Is that clear? Right? I mean, you know, as you can see in this example, both omega d1 and omega d2 seem to be doing a, you know, a reasonable job of making the system stable. But clearly we see that omega d1 is obviously a much better, I mean, is doing a better job of making it look like a first order system when compared to omega d2, correct, alright. So, now the question is, how do you quantify it? How can we, I mean, yeah, can we think of ways in which we can, we say visually it is apparent, okay. The question is, you know, we are in engineering, right, we would like to attach a number to everything. So, what can we do? The third order system, okay, very good, and okay, you compare it, and then what? So, what will you do again, come again? So, you will take a third order system, okay, you will take this compensated system, then you will draw the Bode-plot of a true first order system, right, with the same pole frequency, correct. The true first order system will basically will have you know something like that, correct. And then what will you do? I mean, basically what you are saying is you will measure the magnitude of the loop gain function at which the Bode-plot of the higher order system deviates from the actual true first order system, correct. And if the magnitude is smaller, it is a better approximation to a true first order system. Does it make sense? Okay. Is that clear or no? Alright. So, unfortunately, it turns out, I mean, if you have to do this in practice, what practical difficulties do you think this will lead to? Okay, I mean, let's say you somehow make a first order system with with omega d1. Okay, the problem with magnitude measurement is that at the frequency where the response of the first order system deviates from the higher order system, the magnitude is very small, right, and therefore making any sort of measurement on this becomes fundamentally difficult. Okay, all right. But fortunately, it turns out, and you should have seen this in your classes before, but let me draw your attention to the following. So, let us say you have a single pole system, right, 1 by 1 plus s by omega x, and you would like to measure, you do not know what omega x is, you only have a low frequency sinusoidal generator with a frequency omega 1. You are in a lab, you are told that inside the box is basically a system with a DC gain of 1 and a pole frequency omega x, right, 3 dB bandwidth omega x. I have a low frequency sine wave omega 1, right, where I know that omega 1 is much smaller than omega x. How will we find omega x? There are many ways of doing this. How will we find omega x? Okay. So, basically one way is to say, well, I will plop in this sine wave, look at the output. What is the magnitude of the output? 1 by square root of 1 plus omega 1 square by omega x square, right, that is the magnitude. I will measure the magnitude, and from this I will be able to calculate omega 1 by omega x. Okay. So, now, so this omega 1 by omega x is a small number, right, which basically means that basically the magnitude response is looking like this. Okay. At DC, what is the slope of that magnitude response? It is actually 0, right. So, if you measure the magnitude response at omega 1, right, okay, the slope is very small. So, if you make a small error in measuring the amplitude, what comment can you make about the error in measuring omega, the center frequency, I mean the omega x? It will be very high, correct? Does it make sense, people? Okay. On the other hand, what is the angle of what is the phase shift between omega, the input and the output? Minus tan inverse omega 1 by omega x. For small omega 1 by omega x, what the tan inverse is approximately, this is approximately minus omega 1 over omega x, correct. So, this is so which is more sensitive to omega x? The magnitude falls off like this. What comment can you make about the phase lag? It is linear, correct. So, which makes more sense to use it makes a lot more sense to use phase rather than magnitude, right, because the effect of a pole therefore is visible way earlier in the phase plot rather than in the magnitude plot. Okay. All right, I don't know how many of you have done this undergrad experiment where you build a filter. Let's say you build a band pass filter and you have to measure its center frequency, right. What is the dumb way of doing it? You go on changing frequency, look where the magnitude peaks, and then right. Okay. But the problem with that is that whenever the magnitude peaks, its derivative is 0. So, you change this frequency, it looks like all the magnitude looks largely flat, correct. So, you are not able to make a good judgment. However, if you look at the phase, it turns out that the phase will be varying most rapidly at the center frequency. So, if you just look at the phase shift between the input and output, you will find it is extremely sensitive to center frequency, which is basically what you want, right. So, you will be able to accurately measure the center frequency, right. So, the moral of both these stories is that the phase is a lot more sensitive function of frequency than the magnitude is. So, the effect of these higher poles on the magnitude occur only at omega naught, right, but the phase basically occurs at, the effect on the phase occurs at a much earlier frequency. So, for example, so a convenient way of measuring the phase, I mean basically we want these higher order poles to be far away from the unity gain frequency, correct. You want them to occur way after this has become, the magnitude of the loop gain function has become 1, right. So, a way of measuring how far these extra poles are from the unity gain frequency is to simply measure the phase shift caused by these higher order poles at the unity gain frequency, not at omega naught. I mean, at omega naught they cause 45 degrees each. That doesn't make any sense, right. So, basically we want to look at, to figure out how far these extra poles are from the unity gain frequency, we need to measure the phase of the loop gain function at the unity gain frequency, right. The phase will consist of two parts. One is that due to omega d itself, right. The dominant pole frequency will add some phase shift. How much phase shift does it add at unity gain? It basically adds minus 90 degrees. If there were no higher order poles at all, then this would be a true first order system, and the angle of the loop gain at the unity gain frequency would be exactly minus 90 degrees, assuming that 1 by a naught cube f is very, very large, right. Now, if there were these extra guys at omega naught, the phase shift would be, what would be the phase shift at the unity gain frequency? Yeah, so basically the phase lag would be more than 90 degrees, right. So, if the loop gain function is a naught cube f over 1 plus s by omega d times say 1 plus s over omega naught the whole cube, right, then at the unity gain frequency, which is, I am going to call that a naught cube f omega d, the angle of the loop gain, what is the magnitude of the loop gain function at the unity gain frequency? By definition, unity gain frequency means the frequency at which the loop gain has a magnitude of 1. So, the magnitude of the loop gain is 1 by definition. The angle of the loop gain function is what? Yeah, you know everything, just plug it in and tell me what it is, man. Minus pi by 2 minus 3 tan inverse at omega u. We have already called that omega u, no? That is all, omega u over omega. Okay, all right. And so, clearly as you see, sanity check, as omega naught tends to infinity, what will you get for the loop gain, I mean for the angle of the loop gain at the unity gain frequency? Minus pi by 2, right. The higher and higher the unity gain frequency becomes in relation to omega naught, you see that this phase lag becomes more and more negative, right. And at what point do we start becoming very worried? we know that when the angle of the loop gain becomes -1 at the unity gain frequency, the loop gain then becomes -1 and the closed loop gain becomes infinite, which means that the system is unstable. Does it make sense? Is this clear? So, this basically summary is that the angle of the loop gain at the unity gain frequency right, all right, basically quantifies the separation between UGB and let me call this omega u, between omega u and the higher order poles. Okay, and so we know that the danger mark is basically 180 degrees. Okay, and so the the closer the loop gain, angle of the loop gain at the unity gain frequency becomes to 180 degrees, the more we need to be worried about instability, right. So, a way to quantify that is to actually look at the difference between 180 degree phase lag and the actual phase, right. So, if for a true first order system, that difference would be how much? 90 degrees, because 180 degrees is the phase lag is the danger mark. The first order system will give you a phase lag of 90 degrees. So, the difference is 90. Now, if you have extra higher order poles, what comment can we make about that difference? It will be less than 90. So, that is what is called the phase margin. Okay. So, we will continue in the next class.